All right, welcome to Bootcamp for problem solving conversions and formulas. This is tutorials that are basically designed to help you with general chemistry and physics, these kind of classes of physical science where you need to do some calculations. And our goal here is just to get you up to speed in your background in algebra and conversions and doing dimensional analysis. So as you start your class, this will come easily to you, or a lot easier. So today we're going to start working on solving conversions and formulas. We're going to just get you introduced. But before you proceed, pause this video and go retrieve your writing utensils, paper, and a calculator. And when I say writing utensils, I mean writing with a W. Not writing, but writing utensils, paper and a calculator, so you're ready to rock and roll here. So one of the obstacles that's going to happen when you first start talking about general chemistry or physics is scientific notation. It's just a way to write numbers that are really big. For example, the speed of light is 3 times 10 to the 8th meters per second. All right, if you think about that, that's 3000. Long story short, it's 300 million meters per second. If you're to write it out in decimal notation. All right, we use light in science. We use it to analyze species in chemistry. We shine light through chemicals, and the amount of light absorbed will determine the concentration. But if you made a mistake in writing down one of those zeros in decimal notation, that could be a huge problem, okay? When you're actually you could be off by a factor of 10, or if you forgot a couple of zeros, you're off by a factor of 100. So when you write it in scientific notation, it avoids causing those kind of errors. The other thing is you might have things that are very small. For example, sometimes you hear the term parts per million when you talk about pollutants. So 5 times 10 to the minus 3, if we were to write that in a decimal notation, it's 0.005. 5/1000ths of a gram, or if you said it in milligrams, it's 5 milligrams per liter, or 5 parts per million. And that's a concentration of metal in water, for example, that might be toxic if you're drinking it. So the EPA might need to monitor that. This is a picture of a toxic waste stream below the California Gulch here in Colorado. And you have to monitor the metal content in there. So really the design of scientific notation is that you work with very large and very small notations. This avoids having problems. And it also allows you to quickly estimate your answers, and I'll explain that a little later. So let's talk about how you get to scientific notation. What does 3 times 10 to the 8th mean? Well, basically it means that you're going 3 times 10 times 10 times 10 times 10. You're going 10 times 10 8 times, and every time you go times 10, it's like moving the decimal over once. So basically what you're doing is you're moving over the decimal 1, 2, and if you kept putting zeros on there, 3, 4, 5, 6, 7, 8. So if I looked at it in decimal notation, the decimal started here, and if I moved it 8 times, 1, 2, 3, 4, 5, 6, 7, 8. Well, let's stop right here and make some important notes. Look, if you move the decimal twice, that's 100. So anytime you see times 10 to the 2, that's 100. If you see times 10 to the 3, that's 1,000. Times 10 to the 6, that's the next important stop, is 1,000,000. And times 10 to the 9, that's 1,000,000,000. And a lot of you guys need that number so you can keep track of your money, I'm sure. All right? So when you talk about scientific notation, this is for negative numbers. Nothing's different. And remember, in science, a negative number, it gives direction, is what it's for. So a lot of times if you wanted to say, hey, I'm heading north at a certain rate, and I now want to turn south, I might put a negative sign on it. So it gives direction. It doesn't necessarily mean a quantity that's less than 0. Sometimes we think of that on a number line. But if I have to represent a large negative number, something that's going south very fast, for example, same rules apply. It's times 10 to the 3, so I move the decimal over 1, 2, 3 times. and then just slap that negative sign on there. All right? Another thing you'll see, though, is sometimes the negative sign's out on the exponent. Now, this is different. In mathematics, that means that you're dividing by 10 twice. Anytime you see something raised to the power of a negative sign, it means you're dividing by. So I'm actually taking 5 divided by 10. That's going to move the decimal once to the left. And you divide by 10 again, it's going to move the decimal twice to the left. So the decimal notation would look like this. Okay. So if I start here, we're starting 5.0. I move once to the left, then twice. That's 0.05, which we'd write in scientific notation 5.0 times 10 to the minus 2. Now, a lot of times in scientific notation, you just leave one integer to the left of the decimal mark. And that just is a courtesy. It's almost like you shake somebody's hand with your right hand. It's just a courtesy. And I'll show you some examples where you're not specifically trying to leave one decimal to the left, and there's reasons for that. But for right now, just so you know, when you're writing scientific notation, the traditional thing is to leave one integer to the left. All right, so let's see what we've got going here. If you see it's a positive number, that's a big number. You move the decimal to the right. If it's a negative number, it's a small number, less than 0, you're moving your decimal to the left. And if you're trying to make the number itself negative, you don't put it on the exponent, you put it out here in front of the number. So here's an example where you now have a very small negative number. So once again, you go over here to see which way you move your decimal. You move it to the left and you move it 4 times. So I start right here, 1, 2, 3, 4, and it's a negative number. You put a negative sign on there. So now let's just talk about decimal point placement. What if I just want to move the decimal point to the millionths place, for example? So I basically want to move the decimal. How do I change the notation? The thing to keep in mind here is I'm expressing the same number a different way. So remember what we talked about earlier. If you move the decimal 6 times, that's a million. So now I've made it from 10 to the 8th, right, to 10 to the 6th. So that's 100 million. I made it to just a million. So the number got smaller, right? And I moved down 2 decimal places. So to keep the number the same, this has to move the decimal to 2 decimal places to the right to make it larger. So now stop and look at what I've done here. I basically re-expressed the same number by making this, right, 100 times smaller. I've now made this 100 times larger, so the number is the same value. It's just re-expressed now, so I use 10 to the 6th. And once again, you'll see a reason for this. Now, I've broken with that traditional way of expressing the scientific notation with just one integer to the left, but that's on purpose. Sometimes there's a reason to do that. All right, so now 5.2 times 10 to the minus 5. Let's say that we want to convert it to e to the minus 2, or times 10 to the minus 2. And this e, I've just thrown this out this time. I'll explain it a little bit later, but sometimes on a calculator, instead of saying times 10 to the, you'll see an e or a double e, which represents scientific notation. So I'm now going to convert this times 10 to the minus 2. So now the number's actually getting larger, because here you divided by 10 times 10 times 10 times 10 times 10 is 5 times. Here you're only dividing by 10 times 10. You're dividing by 100. All right? So now the number got 3. It moved 3 decimal places up from minus 5 to minus 2. So now if that is getting larger, then this number has to get smaller by the same amount. So if I move the decimal from here, I move it 1, 2, 3. It's the same number. This number is equivalent to this. What have I done? I've re-expressed this number that was times 10 to the minus 5 as times 10 to the minus 2. It's the same number. Here's some examples for you to practice on. See if you can do this. If you have to, back up the video, run through that explanation again, till you're comfortable, and see if you can answer these problems. So at this point, pause the video, try and do these on your own paper, And when you're done, start the video again and we'll check your answers. So how did you do? Here's what I have for the answers. And just quickly, this is a very large number, right? So I take the decimal where it was here, right? And I'm going to re-express it by going 4.3 times 10 to the 7. That's how many times I had to move the decimal to get it from 4.3 all the way out here to decimal expression, right? Because it's a very large number, but it's a negative. The number itself is negative, so I put the negative in front. This is less than 1. It's a very small number. Okay, so it's going to have that negative exponent. Same here. All right, now we're going in reverse. We're taking a scientific notation expressing it as decimals. And the last one is just more exercise and just can you re-express the same number with different exponents? Shortcuts to calculations with exponential notation. This will help you a lot. It'll quickly allow you to zoom in and see if the order of magnitude of your answer is correct. It'll help you especially perform well on exams where you can really look at your scientific notation and quickly check your answer. So in order to do that, you got to go back and look at a mathematical idea, and that is whenever we write mathematical expressions, we follow an order of operations. Now, parentheses is just thrown in. That helps us to have control over things. But in terms of the bigger action that a function has on numbers, exponents have the most effect on numbers, right? If I take 2 and I cube it up, it's 2 times 2 times 2, right? It's much larger than multiplying and much larger than adding. Okay? But as far as exponents and roots are the same priority, multiplication and division are the same priority, and addition and subtraction are the same priority. And sometimes you hear this, please excuse my dear Aunt Sally. That's just a reminder of the order of operations, that do parentheses first, do exponents, which includes roots, next, do multiplication, division next, addition and subtraction next. And we use this to help us with some shortcuts for scientific notation. In order to do a shortcut with scientific notation, when you operate on the exponent only, drop one order of operations on the power, just the exponent only, and work. So let me show you what this means. Okay, let's do an example. Here we have scientific notation, 2 times 10 to the 2. And we're powering it up. If I was just, now all I'm going to do is operate on this. This number in front operates normally. So it's 2 to the 3rd power. That's 2 times 2 times 2. That's 8. So that's done. So it's 8 times 10 to the, now what do I do with the power? So this is powers, right? That's exponents. Drop one order of operations, that would be multiplication. So now just take 2 to the 3rd power and then multiply that out. And there's your shortcut. So see what I did where I dropped one order of operations when I'm working on the power? All right, let's see another example. Okay, here we're multiplying. Multiply as you would in front. That's normal operation, 8. These powers are being multiplied. Drop one order of operation below multiplication. That's addition. So just add them. So it's 8 times 10 to the 8th. All right? Now, if you worked it out long ways, you could see how that's true. This is 200. That's 4 million. You multiply it together. It's 8. And then you add all your zeros, right? 800,000. But if you do it this way, you can quickly get to that and say, okay, 4 times 2, that's 8 times 10 to the 8th. See how I drop? That's being multiplied. So drop one order of operations and just add it. There's your shortcut. Here's division. Okay, if I was to work this out, longhand, it's 10 times 100. It's 1,000. Divided by, remember the 6, the power of 6 is 1,000,000. Divided by 2 million. So it's 1 divided by 2, and then actually it's going to be much smaller than 1, right? You could cancel out all these 3 zeros, right? You get a number 0.005. Now we can quickly get to this and leave it in scientific notation by simply 10 divided by 2 is 5 times 10 to the 2 divided by 6. If I were to drop one order of operation, I'd subtract it, which is 2 minus 6, which is minus 4. So the shortcut would be 5 times 10 minus 4, which is what this number is. See how I dropped one order of operations? So here's one last example, and this is the one where this shortcut is not as necessary, but there is a way to do this. Now we're going to add this, okay? So if I worked it out longhand, I'd do 10 times 100 and get 1,000. This would be 2 times 1,000. That would give me 2,000. If I added them together, I get 3,000, and that's fairly straightforward. 3 times 10 to the third. All right? So let's get to the same power. This is 1 times 10 to the third, and so to rewrite this, this is where it comes in handy that you can re-express this as times 10 to the third. That way, they're both in the same power. So 10 times 10 to the second, if I re-express this as 1, I made that 10 times smaller, so that has to get 10 times larger. And now these are both the same power. And what do? 1 plus 2. What's the order of operation below addition? There's nothing below addition, so don't do anything to it. That's kind of the reminder. So 10 to the third plus 10 to the third, right? You don't do any change to it. So this 1 plus 2 is 3 times 10 to the third. So long story short, when you're adding exponentials, get them to the same power, operate on what's in front, 2 plus 1, and then leave the power alone. All right? So once again, here's your chance to practice. You're going to look in here, you're going to see, and the important thing to do is identify first what's being done. This is addition, multiplication. Even though there's powers in here, the operation between the two numbers is division. Here you're doing subtraction. Here you're raising it to the power, raising it to the power. Here you're taking the third root. So now what's the opposite of the third root? Drop down 1, divide. So what do? You take the third root of 125, and then you act on 10 to the 6th divided by 3. That's 2. That's your shortcut. All right, so now I'm going to let you do that. Stop your video, see if you can do this on your paper, work these out, get your practice in, and when you're done, turn the video back on to check your answers. All right, how did you do? Now notice here, when you get done with an answer, you get 47 times 10 to the 2, and in my example, I changed that to made that a little bit larger by making that smaller, so it's 40 times 10 to the 2, so 40 plus 7 is 47 times 10 to the 2. But I might rewrite that in the conventional manner where there's only one digit to the left of the decimal, which is 4.7. Neither one of these is more correct. This is just the standardized method. Okay? I think the rest of these are fairly self-explanatory. Look at how you act on negative signs here. 2 times a negative 4 is a negative 8. No change there. But let's drop down and look at this one where it's a root. The cubed root of 125, what times itself again is 125. Well, that's 5. And then when I take 10 to the 6, instead of taking the root, I drop one order of operations and divide by 3. 6 divided by 3 is 2. So that's actually fairly straightforward. Okay, here's another obstacle that will get in your way when you're doing physics and chemistry is equivalent math expressions. This is great for you to learn. In other words, how do you say the same number different ways? And this comes up a lot. So let's go through this. 8 divided by 2. Sometimes you write division this way, 8 divided by 2. Sometimes you write it, as we stated earlier, by putting a negative exponent on there. That also means 8 divided by 2. Sometimes you write it as a fraction in 2 lines. Sometimes you hear the word 8 per 2 or miles per hour as miles divided by hours. All right? So watch. Here's a way that that's used in science. This is the acceleration rate of gravity, 9.8 meters per second squared. So how could I rewrite that division? Instead of putting that division sign in there, I could say times seconds to the minus 2. That means the same thing. Okay, what about multiplication? Well, we all remember the multiplication sign. Sometimes we put it in parentheses. That assumes multiplication. On computers, the multiplication sign looks like this little star. There's an old school dot running around sometimes. That also implies multiplication. And sometimes if nothing is in there, 3r implies 3 times r. What about roots? Okay, here's the second root. It's assumed if there's nothing up there, that means it's the second root, right? Sometimes you put the 2 in there. Oh, here's an interesting way. It looks like it's raised to a fraction. Okay, when you raise to a fraction, the number on the bottom is the root you're trying to take. And then if you were to put this on your computer, you would raise it. That's what the power is. It's a caret. And then here's the fraction in parentheses. And just to compare, this is the second root. If I wanted to have the third root, there is no shortcut. You have to put the 3 out here, which means you could put it as the fraction. That's the third root. This is, by the way, the number 5, right? 5 times 5 times 5 is 125. Or you could write it in computer notation. And once again, scientific notation. Here's what we just went through. But when you look on your calculator, you might see an E sign. And that's 8, e to the 4th. That means 8 times 10 to the 4th power. Sometimes you see a double E. That's 8 times 10 to the 4th again. Now don't confuse this with the little e, which means that is a mathematical notation. That's an anti-logarithm. Okay? So here's another way you could write scientific notation. And here's another example. And sometimes you'll see this is 8exp4. That's another thing you might see in a calculator key. Okay, so sometimes you want to mix powers and roots. So here what we're doing is we're raising 4 to the 3rd power, which means 4 times 4 times 4. And then we're going to take the square root of that. And if you put that all together, 4 times 4 is 16. Times 4 again is about 64. If you took the square root of it, what times itself makes 64? Well, that's the number 8. Right? So with this fraction notation, you can mix both powers and roots. All right, obstacle 3. Here's something that's really important. When you're doing science, when you're doing physics, you're doing chemistry, you should really understand what is being measured. So what I would recommend is as you get into physics and chemistry, I would spend some time with this table, carry it around with you. I'd print it out. And whenever you're talking about something new in class, some of it's going to be stuff you already know, like mass, how much stuff. It's weight in grams. It's a fundamental unit, okay? Time, you understand that. It's how long, right? Standard unit second. It's a fundamental unit. You understand probably length. Sometimes you call it width or how tall something is, right? It's just one dimension. Standard unit is the meter. It's abbreviated to M. That's a fundamental unit. So you understand these. But as you get into class, you might learn something new like acceleration or force or pressure. And you're going to get a description of it. And when you learn that, make sure you understand kind of how you describe it yourself, okay? Make sure you understand the units. And a lot of these units, these more advanced units, are derived from the fundamental units of mass, length, and time. In fact, I don't think I have. Maybe there's one other fundamental unit of here of an electron, which is something specific to chemistry. It shows up in physics as well. But beyond that all these are derived from those fundamental units. And it's really good to learn how they're derived. So I would recommend, once again, just get this table, get it printed out, carry it with you through the class, and as you build this and you learn some new unit like acceleration, okay? Or maybe force is a good one, because this is a good example of something that has a unit itself of a Newton. Or what we use in the English system, we actually use pounds. That's a force. It's a push or pull on matter. So learn how you would describe it so you understand it, so you can conceptualize it. Understand the unit, the stacked unit, the combined unit, but also don't forget what it arises from, what the fundamental units are. See, the Newton has components of mass, length, and time squared. And we just learned that actually means divided by time squared. And that will really help you a lot when you do dimensional analysis. And that, you'll see more of that as we go along. All right, so I'm going to go back here. The reason I highlighted this was these are the fundamental units. And once again, I probably should have highlighted the electron, which is also kind of a fundamental unit. Okay, the next thing is, whenever you're looking at a problem, you need to identify whether something's a conversion or a formula. And this is where we're going to end up this particular talk today. So let me show you what I mean. A conversion is, and it all is back to that table I just talked about, do you understand the dimension? So when I have the question, how many millimeters are in 4.5 meters? So the key here is, do you identify that they're the same dimension? These both deal with length. So if I'm asking to express one length in another unit of length, that's just a simple conversion. All right? Now let's look at this. Force is the product of mass times acceleration. How fast would a 2 kilogram, that's mass, object accelerate if a force of 14 kilograms meter per second squared was applied to it? So I'm given mass and force and being asked about acceleration. Those are 3 different dimensions, 3 different qualities. Now this particular thing is not just a conversion, because basically you're getting from mass to acceleration. There has to be a scientific principle that relates those. That's something you'll learn in class. Now, if you take physics, you'll realize that, hey, that's Newton's second law. Force equals ma. You grade your MOS, you get an F. F equals ma. Oh, yeah, mass times acceleration will give you force. And that's not what we're trying to get you through today. What I want you to really understand is, look at the numbers you're given, look at the numbers you're looking for. If they're different dimensions, understand, oh, I need a formula. If the dimensions are the same, they're both length in this case, it's just a conversion. Start with that, and then in future videos I'll show you how to work conversions. That's where we'll go next. And then the video that follows will show you how to plug and chug on a formula. All right, let's do this as an example. What volume does 4 grams of water occupy at 20 degrees C in 1 atmosphere? Wow, look at that. I'm asking about volume, that's how much space something takes up, but I'm giving mass. Well, once again, that's a formula. There must be some connection between volume and mass. And one of the first formulas we'll learn about in chemistry anyway deals with density, and that's what relates mass to volume. Okay? So, for the following, decide if the problem is looking for a conversion or formula. So we're going to practice again here. How many kilometers are in 2,300 meters? So look what I'm starting with. And all I'm asking is, what's your dimension? Well, this is length. Going to turn it to length. No change in dimensions. That's a conversion, right? So I'm going to let you practice. I'm going to go ahead and run through these other ones and get them all set up. You see if you can answer them. Pause your video. Write down your answers, what you think. Is this a conversion or a formula? And then when you're done, you got your answers down, just restart the video and we'll look at your answers. All right, let's look at the answers. How many kilometers are in 2,300 meters? And remember, know your dimensions not just by the length, mass, and moles, but conceptually. In other words, what is a meter? It's a length, it's a height, it's a width. Understand the concept behind it, not just the unit. So, how many kilometers in 2,300 meters? That looks like that's going to be a length. And this is a length. This is a conversion problem. All right, here's number 2. What volume does 4 grams of water occupy at 20 C and 1 atmosphere? Here's a mass. Here's a volume, right? Not the same dimension, so this requires a formula. Density happens to be a measure that relates mass to volume. That's something you'll learn as you go through in chemistry and physics. Okay? What current, milliamps, is needed to electroplate 4 grams of copper onto an iron ring? Wow, this is 4 grams. That's mass. That's how much stuff, right? Milliamps is current. Wow, those are totally different dimensions. There must be some principle in science that relates, putting down the mass of a material based on how much current is driving that. And by the way, as you get farther in chemistry and physics, you'll understand that current is how many electrons are flowing per unit time. But for right now, today, the focus is, if you identify their different dimensions, there needs to be a formula to solve the problem. And just for your information, if you're interested, it's Faraday's law that relates current to the mass of material that can be reduced in a set amount of time. All right. How many pounds per square inch, which is pressure, and here's what I mean by understanding what pressure is, the true effects of force. That's the definition of pressure. How many pounds per square inch of pressure are in a vessel that registers atmospheres of pressure? This is measure of pressure. This is measure of pressure. This is a conversion problem. So I hope that this has helped at least get you started. This is Bootcamp video number 1. Review this a few times. Make sure you're able to stop and do these problems adequately. Then move on to the next video, Bootcamp video 2.